Hello, students. Let's talk about another drag force example, but now we're going to talk about a falling object. Our approach will be similar to a previous example when we talked only about the horizontal motion of an object. So when we talk about that situation, all we have to deal with is the fact that, let's say this object is moving this way. Well, there's a drag force exerted that way, and that drag force is the net force on this object. In this case, well, it's the net force on this object in the horizontal direction. Okay, so in that previous example, we talked only about horizontal motion. Now we're going to talk about vertical motion. So things get more complicated, so I'll show you how. So an object falls through a fluid, and that fluid exerts a speed-dependent drag force, modeled the same way we modeled previously. This force is linearly related to speed, but in the opposite direction of velocity. So let's say this object, is dropped or is moving, or, let's say is moving, sure. So what we'll have by way of modeling forces, we've got the object's weight and we've got BV. Okay, so we start these sorts of analyses with Newton's second law. So this says, well, this object will accelerate this way until it doesn't, right? So, let's maybe back up a step. So what happens here is when this thing is initially dropped, here's what we get. Velocity is 0, drag force is 0. Later, as this thing speeds up, drag force gets bigger. Quote unquote, later, we get to this case where here's mg and here's drag force. We get to a case where these things get to be equal and opposite. And, well, that velocity we call v terminal. The velocity at which this object no longer accelerates, because the drag force has gotten to be the same size as object's weight. Okay, so let's generically take a look at an object at some instant like this, let's say. So here's net F, mg minus drag force equals ma. Come on now. So these types of situations, well, what we have is, if we write A as its definition, the instantaneous rate of change of velocity, we have a, rate of change of velocity that's dependent on the velocity. Okay, so this is the differential equation that we're going to have to solve. And the methods are similar to what we've done before. We're going to end up separating these variables. Okay, but I want to talk to you about some specific approaches that I found that make things easier to handle. Well, first thing is, what we're going to have to do is, as we mentioned, we're going to have to do what we call separate these variables. So I'm going to multiply both sides by that dt, and we'll get this mg minus bv dt is m dv. This will allow us eventually to integrate each side, except what you may notice is we've got, this is a variable, right? Velocity is variable, and here we'd look to integrate with respect to that variable. So what we need is all the stuff with v in it on one side, and best practice probably is to get everything else on the other side. But I want to show you this. One thing that I've found is helpful, and it's algebraically helpful, but also physically maybe enlightening, is to, well, look, if we were to isolate this v, because again, we're trying to eventually find what is this object's velocity as a function of time. What I'm going to do is, let's get that by itself, that v by itself. So we get this mg over beta minus v dt is m over beta dv. Now, so this is the variable this variable velocity we're trying to write the expression for. But look, this, and we'll see this in a different unit also, this combination of constants, those things are all constant, has a physical meaning. Okay, and that physical meaning, if we look here, is that at V terminal, when we get to V terminal, well, what it means is that beta V equals mg. Beta V terminal equals mg. So mg over beta is, the physical meaning of that is V terminal. All right, so not only does this sort of clean things up algebraically, V terminal minus V, it gives us some insight into the physical meaning of a combination of constants. Mass, come on, mass over beta dV. Now, remember, we have to get, come on, all stuff with V on the same side as the stuff with dV. So to do that, I'm going to divide both sides by this term. I'm going to move this stuff to the other side, so here's what we get. Let's see, Vt minus V. Nope. 1 over, thank you, dV. Now, what I've noticed already is I've made a mistake, all right? And let's step back for maybe a brief minute. Nope, I'm going to do it later. I'm going to do it later, okay? Because it's a good mistake to make, and I want to talk about it in a bit. So now what we have is all stuff with V over here and dV and other stuff over there, and there's no way for me to move this VT over there. I've got to leave that where it is. But what I do want to do is I'm going to make sign stuff work in my favor. So here are my recommendations. All right, recommendations. 1, isolate the variable and re-express the constant combo, right? So here's our constant combo, right? And we get to re-express it in terms of its physical meaning. 2, I'm going to say change sign in your favor. Come on, your favor. And so I don't want to have to integrate, because what we're going to do now is integrate both of these sides. I don't want to have to integrate with the negative. It's just one more place to make a sign error. I've already made a sign error. I'll show you later. So I'm going to do this. Let's multiply everything by -1. And we get integral of negative b beta over t dt is integral of, look, v minus vt. That's easier. Okay. Now, these variables have limits, right? So we're going to say that, well, this time will start at 0, and when we get to time t, well, this thing was dropped at a speed of 0 initially, and it gets to some velocity v at time t. Okay, now whether or not, let's see, you might or you might not recognize this integral on the right side is, or left side, excuse me, is easy peasy. All right, we get that evaluated from 0 to t, so is just negative, sorry, that's not right, m, thank you, m, there's your integral evaluated from 0 to t, so we simply end up with that, yes, pardon my mistake. Now this side, if you want to be formal, we can say, you know, let's say, we could do like a u substitution perhaps if you'd like. You probably don't need to, but the u sub might look like this. Let's say let u equal the stuff in the bottom, and then we could say, well, du dv is, well, the number 1, and therefore du equals dv if we multiply both sides by dv. And so this thing really turns into 1 over u du. And many of us know the integral 1 over x dx, or in this case 1 over u du, is the natural log of u. Thus, nope, do it again. Come on. Well, this is actually the natural log of v minus vt. Where we evaluate, remember, now we go back and put our limits in, we evaluate from 0 to v. Okay, so let's evaluate. This gives us, yep, fine. Let's see, the natural log of, put v in for that, v minus v terminal, minus the natural log of, put 0 in for that, negative vt. Properties of logs say that we can turn this into the natural log of v minus vt divided by negative vt. And we're trying to solve for this v, so now we're going to raise both sides, or we're going to e to the both sides. E to the natural log of that stuff is that stuff. We're getting closer. Wait, now wait a minute. Did I make? Hang on, pause please. Yeah, on the upside, I realized I didn't make a sign error before, so we're all good. So let's see. Now we're going to solve for v. So negative v terminal e to the negative beta t over m equals v minus vt. Add vt to both sides. We get v. This v as a function of t really is v terminal minus v terminal e to the negative blah 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 blah. Typically what we'll do here is factor out that v terminal, 1 minus e to the negative beauty. There it is. There's our expression for velocity as a function of time. Okay, so what's this look like? Well, boop, boop. V as a function of time. Well, let's see. V of, let's see, what's V naught, right? V at time 0. It should be, let's see, it's V terminal 1 minus e to the 0. E to the 0 is 1. So it's 0. Right. We said we dropped this thing from rest. Yeah. As t approaches infinite, v approaches v terminal 1 minus e to the negative infinity, which is 1 over huge, right? That's 1 over e to the infinity. It's enormous number, which is approaches 0. So this approaches v terminal. Okay, so this function approaches some v terminal, which, if we're being explicit, we can go all the way back up and say, well, oh yeah, here's our v terminal, mg over beta. So we can say this function asymptotes here, and we get a limited exponential growth that looks like that, where this velocity approaches but takes infinitely long really to get to that terminal velocity. So here is your expression. Fair? Fine? So I just want to reiterate a couple of these steps. One, and you don't have to do this, and believe it or not, I found that my students don't necessarily take my advice when we do this, but it sure works for me. It cleans up algebraic stuff when we do this. It also gives us some insight into physical meaning of this is supposed to say constant combos. Constant combos. Okay, like in this case, right? And the reason we're doing this in one case is we'd really like to isolate this variable that we're trying to write an expression for that allows us or gives us a way of saying, ooh, that means something. Okay. The other thing I recommend you do, right? Here's a place where if you were to not do this and you did a u sub where u is vt minus v, then there's a negative sign, and you have to, when you integrate, you have to make sure you undo that. So I really recommend that you change, quote, change sign, quote, in your favor. So instead of negative v, we just get v, and then the rest is, the rest is calculus, algebra, a little evaluation. Okay. What's certainly worth doing, I bet, is to say, okay, well, if that's the velocity function, right? We have v as a function of t is v terminal 1 minus e to the negative bt over m. Well, what's this thing's acceleration as a function of time? Well, it's the instantaneous rate of change of that velocity function. So let's differentiate this function. Okay, well, what do we get? We get, this is really like saying, let's see, it's like saying let's differentiate vt minus vt e to the negative beta t over m. So this is a nothing because that's a number. So we need, let's see, we differentiate this part, right, with the negative in it. This part with respect to time, we keep what we start with. And then we have to chain rule, perhaps? Differentiate that part with respect to time, which gives us a negative beta over m. So let's see, that's, well, positive beta vt over m e to the negative beta t over m. What's this stuff again? Oh, there's a constant combination, right? Now let's see. We've got this mg and this beta v terminal being the same size. This says beta v terminal is mg. So look at this, beta v terminal over m, right? This stuff. Guess what? It has some physical significance. It's g. Oh, yes, look at this. This object's acceleration as a function of time goes like this. Oh, that is gorgeous. All right, so what this says is, here's object's acceleration as a function of time. That, well, let's see, a at time 0 is g e to the 0, which is g. This thing starts at g, and as time goes on, this acceleration approaches g to the e negative infinity, or g over huge number, which approaches 0. So this is an exponential decay that does that, approaches 0. So look, right, we have initially big rate of change of velocity, later smaller rate of, later even smaller, and sure, big rate of change of velocity, smaller. Right, notice we've called downward positive, so like, this slope is positive, this value is positive, this slope is less positive, value less positive. Not bad, eh? All right, folks, there's a lot there, isn't there? Woo-wee! But what we need to recognize is there are functions where there are expressions that we can generate via Newton's second law or via some sort of analysis, in these dynamics cases via Newton's second law, that show us that the rate of change of a function is related to the function itself. All right, in those cases, it is most likely, in those cases, what will happen if the rate of change of function is related to linearly to the function? Well, what you get is an exponential solution. Okay? And I won't reiterate my recommendations again, but here's one of the points is this analysis is entirely analogous to an analysis that we'll perform when we talk about electricity and magnetism, where it's not velocities and rates of changes of velocities that are related, but a different quantity. There are lots of situations in which the rate of change of a quantity and the quantity itself are linearly related, and all of those situations will yield exponential either growths or decays. Limited exponential growths or decays. Or it might be an unlimited exponential growth, but not for us. Okay, thanks folks.